Hello everybody, hope everybody is doing great. In this video, I have got a couple of questions that deal with the concept of work and energy. We will learn work energy theorem in quite some detail, but before I begin with this lecture, I'd like to share a question with you. The result could baffle you, so be careful about it. I have a sphere that does not move. On the sphere, there is a tiny pebble, and this pebble is given a small nudge and the pebble starts sliding down. The question to you is, at what angle with the vertical theta does the tiny marble leave the surface of the larger sphere? That's the question to you. At this stage, I'd like you to pause the video and think about the possible answers. But if you haven't solved this problem before, and if you're solving it for the first time, the result could be really fascinating. With that note, let me begin with today's video. Let me demonstrate to you what is work energy theorem. Whenever a work is done on a system, the work transforms into change in kinetic energy. So you can write that as the work done on the system is W, that's equal to half mv square, where m is the mass of the body, v is the final velocity attained by it, and half mu square, u is the initial velocity. As you can see, half mv square is the final kinetic energy, half mu square is the initial kinetic energy. The difference between them becomes the work done. Now, in case of a constant force, the work done is simply calculated as force acting on the body dotted with the displacement. So you combine these two equations, you will have F dot D equal to half into M, pulled out as a common factor. Inside the brackets, you will have half mv square, v square minus u square. Now this is the expression for work done by a constant force. There can be a lot of questions based on this concept in the competitive exams. One such question that appeared in AIMS 2010 is something that we will discuss next. So let's look at the question. A cord is used to lower vertically a block of mass m by a distance d with a constant downward acceleration of g by 4. So what you have here is a block. The block is acted upon by a tension in the upward direction. Obviously, the weight acts in the downward direction. Let me write it as m into g. The downward acceleration of the block as a result is g by 4. If it's accelerating downward, that means mg would be greater than t. You can write mg minus t equal to m into acceleration. In this case, it's g by 4. So what would be the tension? Tension would be equal to mg minus mg divided by 4, which is 3 mg by 4. That's the tension in the string. Once you know the tension, dear friends, is the force that's acting on the block. And the question says that the displacement of the block in the downward direction is d. It's quite easy to calculate the work done. The work done would simply be equal to force dotted with displacement. Now, force is tension, displacement is d, and the cos of the angle between them has to be written. Do you see that the force is tension, it acts in the upward direction, and the weight acts in the downward direction? The angle between them is 180 degree. So cos 180 degree is how you compute the work done. The work done would be equal to T, which is mg multiplied by d divided by 4, because mg by 4 is tension. Cos 180 is minus 1, and that becomes your work done. This question is as simple as this. So when you know how to apply work energy theorem, how to calculate the work done, this is a very simple question to calculate the work done, and this is how you would do it. Let's look at the next concept, which is work energy theorem for a variable force. We have looked at how to apply work energy theorem in case of a constant force. One tiny thing that's going to change in this case is that the force acting on the body does not remain a constant. So you cannot write work done is equal to force times displacement. You cannot write this. Then what is to be written? You can say that there is a force that causes an infinitesimal displacement in the body, and this tiny displacement that the force is causing does an infinitesimal work on it, and dw becomes equal to f dot dx. Now this is how you would calculate a tiny work done in moving the body by a tiny amount. If you want the total work done, then this function, which is f in this case, should be a function of x, and the total work done would simply be equal to an integral of f dot dx, and it must be integrated from some initial position to final position x. Even in this case, the work done would be equal to change in kinetic energy, so that is half mv square minus half mu square, which can, both of these equations can be combined, and you will have integral of xi to xf equal to of f dot dx would be equal to half m multiplied by v square minus u square. This is the expression for work energy theorem in case of a variable force. Now, having understood this little bit of physics, we will continue to solve another question. This question had appeared in a competitive exam. Let's see what the question says. A force acts on a 30-gram particle. So the mass of the particle is 30 gram. 30 gram is 10 to the power of minus 3 kg, in such a way that the position of the particle as a function of time is given by x equal to, I'll write the higher order terms first. So it would be t cube minus 4t square plus 3t. This is the equation for position of the particle, where x is in meter and t is in seconds. What is the work done during the first 4 seconds? That's the question. What is the initial time? 0 second. The final time, dear friends, is 4 second. What is the work done during this period is the question to you. Let's try and figure out. In order to calculate the work done, we understand from work energy theorem that change in kinetic energy is the work done. So let's find the kinetic energy in each case. The finite kinetic energy at t equal to 0 and kinetic energy at t equal to 4 second. The initial kinetic energy can be calculated only when you calculate the velocity. So differentiation of position should give you velocity. Let's begin. The initial, the velocity equation would be dx by dt. That's equal to 3t square. Differentiation of t cube is 3t square minus 8t plus 3. This is the equation for velocity. If you want initial velocity, u would be equal to 3 multiplied by 0 square minus 8 multiplied by 0 plus 3. So the answer for initial velocity u would be 3 meter per second. 3 meter per second. That's the initial velocity. Going further, on similar lines, you can calculate the final velocity. The final velocity v would be equal to, put t equal to 4 in this equation, 3 multiplied by 4 square minus 8 multiplied by 4 plus 3. Now this is going to be 16, 4 square is 16 multiplied by 3 would be 48 minus this is 32 plus 3. So the answer would be 19 meter per second. This is the final velocity. That is the final velocity. Well, the work done would simply be equal to half into mass into final velocity square minus initial velocity square. So I have half. Mass is 30 gram, 10 to the power of minus 3 kg multiplied by v square, which is 361. 19 square is 361 minus 9, because 3 square, the initial velocity square, is 9. So the amount of work done now becomes equal to 361 minus 9 is 52. 352. 352 multiplied by 15, because 30 by 3 is 30 by 2 is 15, and when you simplify that, you will basically get 5.28 joule. That's the amount of work done, and that's option A. So that's how you get to the answer, as simple as that. Usually when questions are encountered by you in a competitive exam, they can make you really anxious, because you have been taught that the work done is force into displacement, but here the displacement is a function of time. There is no way you can integrate and get an answer, because in work energy theorem I shared with you that integral of force times displacement is work, right? But then this is a question, it's a variant that is a little different, so that's why I came to present to you about this. The regular questions are ones that are easy, you can handle them yourself, but then this was something interesting. Going further, I have another question, but this is related to potential energy. A chain of mass m and length L hangs from a table with 3/4 of its length hanging down. So this length of the chain, by the way, is 3/4 of the total length. That's 3/4 of the total length. Calculate the amount of energy required to pull the chain up the table. That's the question. Now, to begin with, to make everything easy for myself, I will say that the amount of energy associated with the chain as such is 0. The initial energy right now associated with it is right now 0. I have to pull this whole chain up. Now the question is, where is the mass of the hanging part of the chain? You could say, CRS sir, the whole mass of the chain is distributed all the way from the top of the table to wherever the chain ends. But then you must remember that there is something called center of mass. The center of mass of this hanging part of the chain lies exactly at the center. Let me say that that distance, which is the distance from the top of the table to the center of the chain, is h, and that would be half the total length of the hanging chain. So that would be 3L divided by 8. That's the height by which I will have to lift it up, and when I lift it up, the potential energy would increase. And how much would be the potential energy? The potential energy that it would have is the final potential energy, I'll call it PEF, which is mass of the hanging part of the chain. I'll call that small m, maybe capital M, because the question says small m is the total mass of the chain. So capital M here is the mass of the hanging part of the chain, multiplied by G multiplied by H. H is the height by which the center of mass of the chain has to go up, because center of mass is that point at which all the mass of the chain is assumed to be concentrated at. So the whole chain is concentrated at this place. If you can take the point up, assuming that all the mass is here, then you have solved the problem. Let's solve it. The final potential energy is this, but I told you that the initial potential energy, dear friends, is 0. I have assumed it to be so, because we all that we need is to calculate the work done in this case would simply be equal to change in potential energy. That's final potential energy minus initial potential energy, which is mgh. M is 3/4 of the total mass, because 3/4 of the chain is hanging. So I have 3/4 m into the 3/4 m multiplied by G. H is 3L divided by 8. So the answer you have for the work done is 9 mgl divided by 32. Now that's the work done in pulling the chain up. There could be various solutions that will ask you to integrate the tiny amount of work done when you pull the chain little by little, but then this can be treated to be a shortcut. So one must know how to get here. Well, having said that, we will look at the next question. This question, what is the minimum velocity that a pendulum's bob must be given in order for it to complete a vertical circle? So you throw a bob and it just makes a vertical circle and comes down. Question is, how much energy is to be supplied? This is a question in the NCERT textbook as well. So let's address that. When you give the pendulum only a little bit of energy, it starts swinging. You give it a little bit of energy, it starts swinging, a little bit of velocity, and then give it a little more, it swings harder. Give it a little more, it goes to the top, sags, and comes back falling down. But if you give it even more, it just completes a circle. Now the question to us is, what is that minimum velocity you must supply to the bob at the bottom so that it makes a complete vertical circle? Let's try to figure out. I have the circular path taken by the bob. The bob right now is here, and that's the pendulum's thread. Let's assume that the radius here is r, the mass of the bob is m, and it has to get here. Let us assume that the potential energy possessed by the bob at the bottommost point is 0. So the potential energy at this place is 0. So what you do now is give it a velocity. Let's give it a velocity v. This velocity makes it go up and just complete a vertical circle. If it is any lesser than this, it would go up, sag, and fall down. So now this particular bob has traveled to the topmost place. It has traveled to the topmost place. The thread is now this way. Well, of course, that's the center. Here is the center. I just marked the center. Let me call that center O. If you ask me to draw the free body diagram at the topmost point, I just say that the centripetal force in this case is mg. So that's when you know you've given exactly minimum velocity, because at the topmost point, the thread is not helping the bob to go around in a circle. It's just the weight that's providing all the required centripetal force. So when that is the situation, you can say that mg, which is the weight, provides all the centripetal force, and all the centripetal force is mv square divided by r. Let me send the r onto the other side and multiply the whole equation by 1 by 2. When I do that, I have 1 by 2, which has just been multiplied. I have mv square, this thing has been written here, and then I have mgr. I've sent the r there, and then there is a by 2 because we have multiplied half on both sides. Well, half mv square is the kinetic energy of the bob at the topmost point, and we have just figured out that it's mgr divided by 2. That's the kinetic energy at the topmost point. Let me write it as kt. And if you ask me, sir, what is the potential energy? I'll call that U at the topmost point. It is, I said that this is the reference. That is the reference, and potential energy at this reference is 0. The potential at that reference is 0, and it has gone to a height equal to 2r, because from here to here it's r, from here to there it's r, totally it's 2r. Potential energy would be mass into acceleration due to gravity multiplied by height, mgh. H is 2r. So the potential energy of the topmost point can simply be written as 2 times mgr. This is the potential energy of the topmost point. From the conservation of energy, you can say that when the bob comes down, because it comes down back to this place, the potential energy is still 0. The potential energy at this place is 0. Then what did the potential energy, where did the potential energy which it had at the topmost point go? All of that became kinetic energy. So the kinetic energy at the bottom is equal to the kinetic energy at the top plus potential energy at the top, because both of these together become kinetic energy at the bottom, because the potential energy at the bottommost point is anyway 0. Having said that, the kinetic energy at the bottom, let me say, is half mv square, or v minimum, vm square. Vm means v minimum, the minimum velocity which you give, it goes, because if it's coming back, if you give it so much, it would go up, just the opposite of what just happened, right? So the minimum velocity that it would have is equal to the kinetic energy at the top is mgr divided by 2 plus the potential energy at the top, which is 2 mgr. So if you continue to solve this, we have half Vm square equal to, take the LCM and then add the terms, you will have 5 mgr divided by 2. You will see that 2 and 2 will get cancelled. So will m and m. The minimum velocity with which you will have to project it can now be quite easily obtained, because v square m is 5gr and Vm would be equal to a root of 5gr. Now that is the equation that lets you calculate the minimum velocity that you must provide to the bob in order for it to make a complete circle without the thread sagging in between. You need to be surprised here, because irrespective of whatever the mass of the body is, the velocity just remains the same. You tell me the radius of the circle that the bob makes, and I'll tell you how much initial velocity must be given to it at the bottommost point in order for it to complete the circle. A homework for you would be to calculate what is its velocity when you give it this velocity. What is its velocity at any other point, let's say at an angle theta? What would it be, its velocity? You can send me a mail to discuss with me, and we can have a very nice brainstorm about such questions. Anyway, going further, we have the next question, which really is the most fascinating question for this lecture. I discussed with you in the beginning that we have a bob, a tiny marble out there. The marble sits on a sphere that is stationary, it doesn't move. When you give it a tiny nudge, it starts sliding down. The question is, at what angle does this particular bob leave the surface? That's the question to us. At what angle theta does it leave the surface? Well, you will have to now apply work energy theorem to crack this problem, but you will see that's not just sufficient. Just like in the previous case, you will have to draw the free body diagram and analyze. You will have two things that are unknowns, and you will have to write two equations in order to get to the answer. Let's find out how to do that. Well, I have a sphere here. It's quite a big sphere, and a tiny marble that's just trying to fall down, just falling down. It's just about to leave the surface. That happens to be the center. This is the center. Let's say that the bob or the marble right now makes an angle theta with the vertical, and it's just about to lose the contact. It's just about to lose contact. Let's say the angle is theta. Now let's find out what are the forces that are acting on this tiny marble. One force that can be directly identified is the weight. That's m into g. The weight is mg cos theta to this side, because if that is theta, then this also is theta. For obvious reasons, they are alternate interior angles. So mg cos theta is the force that acts towards the center of the circle, and tangential to the circle there is this component of weight, which is mg sin theta, that acts. I know you're wondering what happens to the normal reaction, but then, my dear friends, I said just now that the bob or the marble in this case is just about to leave the surface. At this particular situation, the normal reaction has just become zero. The normal reaction has just become zero, and that's why I haven't drawn the normal reaction. With this situation under consideration, you can write the equation for Newton's laws of motion. Obviously, this particular marble is going round in a circular arc, so it must be under the action of a centripetal force. The centripetal force is always given by mv square divided by r, where v is the instantaneous velocity of the marble right now, and r is the radius of the circular path. And the centripetal force is provided by the component of the weight that acts towards the center of the circle, and that's m into g into cos theta. You will see that m and m gets cancelled. V square can be written as g r cos theta. That's an important equation. We have two unknowns here. We have v, which we do not know. We have theta, that's also not known. The other two are constants. So in order to find theta, you will require another equation. That's when work energy theorem comes into play. Let's try to find out. Well, I have the radius to be r. The radius is r. That's all the way from there to there. But the bob has come down. It was here. The marble was here, and the marble comes down while it's here. It has come down a height r 1 minus r cos theta. The reason is very simple. Watch. If this is r, this is the adjacent side, and that's r cos theta. That's r cos theta. If this is r and this is r cos theta, the length here must be r minus r cos theta, which can be written as r into 1 minus cos theta. That's the height that the bob has lost. I keep interchangeably using bob with marble, so pardon me for that. So we have r into 1 minus cos theta. The potential energy lost by the sphere is mgr into 1 minus cos theta, because r into 1 minus cos theta is the energy lost by it. It's equal to half mv square. Half mv square. This is because all the potential energy it has lost has become kinetic energy. There are no forces that are dissipative in nature. There is no friction. So everything that is potential energy that's lost becomes kinetic energy. So here also I have m and m getting cancelled. We have v square becoming equal to 2 times gr into 1 minus cos theta. Now this is also another equation that we were in need. Let me call this one equation 1 and call that equation 2. Having said that, let's continue with solving these two equations. We have v square on the left hand side, so the right hand sides can be equated. We have gr, okay, we have gr multiplied by cos theta being equal to 2 times gr into 1, 2 times gr. I think all of these are small r's. Really sorry for writing a big r. Okay, so we have 2 times gr into 1 minus cos theta. So gr and gr also gets cancelled. That simply means that the angle, which is theta we are about to find, does not depend on g, nor does it depend on the radius. That's an absolutely fascinating thing, because we thought that it could depend on acceleration due to gravity, it could depend on the mass, it could depend on the radius, but then looks like it doesn't depend on anything at all. So we have cos theta equal to 2 minus 2 cos theta. 3 cos theta would be equal to 2, and this simply implies that cos theta would be equal to 2 by 3. Well, the final statement, theta would be equal to cos inverse of 2 by 3. That means what come may, when the effects of gravity are neglected, the small marble, wherever you do this experiment, be it on Earth, on Pluto, be it in Jupiter, be it on Jupiter, provided you find a surface there, but wherever you do this, the tiny marble is going to leave the surface of the larger sphere invariably at cos inverse of 2 by 3. And that's a fascinating result. So with more numericals and more concepts like this, I'll be back in the next video. It was great talking to you. Thank you so much. May you prosper with respect to these concepts. Thank you so much.